All right, let's jump right back into it. And last time, we made some really interesting discoveries with the angle sum. So we have cosine of a plus b, and also had cosine a minus b. And you guys remember what happened here with the cosine? It has pretty much the exact same structure. You would say cosine of a, cosine of b, but because it is the addition, you would have subtraction there. So down here, because you have subtraction, then you would have the addition. And if you remember where this came from, we used the identity, we changed the b over to a negative b and dropped it in, and we generated the other identity. If you remember that, it makes it a little bit easier to remember this part as well. Okay, we also talked about the sign. Instead of saying cosine, cosine, you would say sine, cosine. Okay, you take the terms, drop it in, you say AB, and then switch it up. BA. AB. And for the sine, I'm going to in order to figure out the sine of the angle of s plus t as well as cosine, what we need to do is trace this back to the angle sum identities. These identities that we have back here. So we see that we have sine of a plus b, so I want to use this. And then likewise, cosine of a plus b, I want to use this. Look at what the identities ask us to find. You got to find sine of a, you got to find cosine of b, and then sine of b, and then cosine for a, for both of these. Well, what we have here is we have cosine of s. What am I missing? I'm missing sine of s. I have sine of t. What am I missing? Cosine of t. So the hunt is on. I got to figure out this, and I got to figure out this. How am I ever going to figure out this value here and this value here? Well, let's get thrown back to the very beginning of the semester when we were doing the exact same thing. But now it's just really two problems baked into a single problem. Sine is going to correspond to opposite over hypotenuse. So you can construct your triangle. So here we have, or in this case cosine, we're going to have the adjacency side. We're going to have hypotenuse. And I got to figure out what's happening here with the opposite side. Well, call it x here for the moment if you like. It's a right triangle. And a right triangle is all right, all right. And something to know about right triangles is the Pythagorean theorem. 3 squared, x squared, 5 squared. Okay? The objective, solve for x. And then take the square root. But whenever you take the square root, what do you have to do? Tack on plus or minus. The common fallacy is if you take the square root of x squared, you get x. And that's not true. Like, what do you mean that's not true? I thought that was always true. Well, what if I took negative 2 and I squared it? We would get 4. And if I take the square root of both sides, does I simply just knock off the square? Would you say that those two things are the same then? No. So whenever you are taking the square root, again, you do have to say plus or minus because the square root of x squared is really the absolute value of x. So I got to decide, am I taking the positive case or am I taking the negative case? Well, the problem says we're going to be in quadrant 1. And in quadrant 1, what happens for sine? Sine corresponds to y, and that's going to be positive. So in this case, we'll just say 4. We're in good shape. So we have 4 and the hypotenuse 5. Okay, now all we're going to do is do the exact same thing, but we're going to do it for cosine of t. And we can construct a triangle, and if you want, put it on a grid system. That's fine. If you really want to see where you're at, that's perfectly valid. This point up here is going to be cosine of t, sine of t. But we already know this point, and we know the ratio. Sine is going to be opposite over hypotenuse. And I got to figure out the adjacency side. So once again, the hunt is on. Call it x. X squared plus 5 squared equals 13 squared. And I do see that we're going to be in the first quadrant, so whenever we take the square root, we'll take the principal square root and not worry about the negative root. If I was to take this and try to figure out the value for x, I could plug this into a calculator. That would work perfectly fine. But how could I solve this, let's say if the calculator fails, or if I didn't bring my calculator? What would I do? Well, first off, take the 5 squared, throw it to the other side. And my question is, what do you see here? I spy with my little eyes between things being squared. Do I know an identity called of squares? Absolutely. Oftentimes when we see difference of squares, we use the identity to factor polynomials. But I can also use the identity to speed through a calculation if I need to. See, if I use this identity, I can say 13 minus 5, 13 plus 5. 13 plus 5 is going to correspond to 18. And then 13 minus 5, that gets you a value of 8. Well, 8 is going to be nothing more than 2 cubed, and 18 is going to be 2 times 9. What happens when you take the square root? If you take the square root here, what you're going to come up with, the square root of 9 is going to be 3. 8 times 2 is 16. That's 4. So you could use the difference of squares identity to crank this thing out if you need to. Or you could do it the more complicated way. Real quick, what's 13 squared? And then take off 25. And then take the square root. What if the numbers start getting bigger? It's going to be more challenging. So this could help out as you go about the problem. All right, so we get 12 down below. Cosine is going to correspond to 12 over 13. Sine of s plus t, we'll take a sine of s cosine t plus sine of t cosine of s. Drop in the 4/5, 12/13, and our 5/13. Here's something to note. Look at your denominators. They're exactly the same here, aren't they? It's a good way to self-check yourself, make sure you're in the right path. So it's going to correspond to 65, 48, 15. Looks like we're looking at 63 over 65. Okay, there's sine of s plus t. Now, I got to figure out cosine of the angle of s plus t. I could use the Pythagorean theorem, but that's way over the top. I know the angle sum identity, and it's going to crank it out a little bit faster. Take everything and drop it in. And notice again the denominator. It's the same. 65. And it should be the same, shouldn't it? Because cosine is going to be the opposite or the adjacency side or the hypotenuse. And sine is opposite side over the hypotenuse. So I should get the same thing there. Otherwise, we're going to be in a world of trouble. Okay, so we're going to get 36, subtracted off 20, 16 over 65. Okay, so when I have these problems and I have a difference, a little mixture of angles, I can use the angle sum identities to take everything and collapse it down to figure out the actual numerical value that I'm after. How would I do this, you think? What's your plan of action? Well, the problem here is this is a 1 theta, that's a 2 theta. So we got a bit of a snag. But guys, how do you make a 2 theta? How could you make a 2 theta? Could you not take sine and say theta plus theta? Because what's theta plus theta? 2 theta. Here I have the angle sum. I can apply my identity for angle sum over here. I could simply say sine of theta, cosine of theta, plus sine of theta plus cosine of theta. It's a little hard to see this, but A and B, sine of A, cosine of B, sine of B, cosine of A. Well, that's pretty cool. Hey, it's the same thing, isn't it? It collapses down. 2 sine theta cosine theta. You know, that looks like it might be kind of important. Do you think we should catalog this? Yeah. Well, let's see. Sine of 2 theta, that's going to be 2 sine of theta cosine theta. Okay. Well, first off, I got to figure out sine of theta and cosine theta in the problem. I have my triangle. We'll have adjacency. We'll have hypotenuse. We can apply the Pythagorean theorem, but we're going to see our 3, 4, 5 triangle. We'll have the opposite sides being 4. And we can apply this nice identity now that came from the angle sum identities. Sine of theta is going to be 4 over 5. And cosine was given to be 3 over 5. In the end, we'll have 12 times 2, 24 over 25. That's pretty cool. Well, what about this one then? The cosine of 2 theta. Well, it worked so well last time. Let's go back and look at the angle sum. What would happen if you made theta as well as b? So if you do that, what's a theta plus a theta? It's 2 theta. So we'll have cosine theta, cosine theta. And A again is theta. B again is theta. So what we get here is cosine squared minus sine squared. That seems rather important too. So cosine 2 theta is cosine squared theta minus sine squared theta. What was that Pythagorean theorem in terms of trig functions? What was that again? Cosine squared theta plus sine squared theta, and then equals 1. So it's close, but it's not quite there, is it? So when you have the difference between cosine squared and sine squared, it's resonating this idea of a double angle for cosine. And that's what these identities right here are referred to as double angles. Yeah? Can you ever guess why they're called double angles? Because you're doubling the angle from theta to 2 theta. Well, let's keep pushing this a little bit more. What would happen if you took the sine squared in the Pythagorean theorem and threw it to the other side? Okay, well, if you did that, what you would get here is 1 minus sine squared theta. And what if you're daring to dream big? Get a little dangerous. Do some math. Take it and plug it in up top. What you would get out of this is you would have 1 minus sine squared, but you're already subtracting off the sine squared. Cosine 2 theta becomes 1 minus 2 sine squared theta. Whoa. What if you did it the other way? What if instead of throwing the sine squared over, you threw the cosine squared over? And you took that and plugged it in up top. Well, you have cosine squared minus 1 minus a cosine squared. Okay, so you take the minus of the cosine squared, that becomes positive. But you already have a cosine squared up here. So you can also take this identity and you can calibrate it as 2 cosine squared theta minus 1. You can also say cosine squared theta minus sine squared theta. So when looking at the double angle identity for cosine, there's just not one I need to remember, but rather it's going to be 3. What you could do is you can do what we just did. You can just memorize this one and then unpackage it. Just remember, apply the Pythagorean theorem, convert all the sine squareds over or all the cosine squareds over into the other trigonometric function. Here are some additional identities that you're going to need to know. The sine of 2 theta, if you're going to be taking a calculus class later on, this thing is golden. This is, I would say, in terms of how it's used in a calculus class, Pythagorean theorem is cream of the crop, and this thing is right below it. This is very, very important. Okay. Now, with that said, we can apply these identities, and we can figure out what's going to happen with cosine of 2 theta. Which one should I use? It doesn't really matter. Pick your favorite one and go with it. Look at the problem, see what's already been provided in the problem. Don't make it more challenging than it really needs to be. So in this particular case, we're given cosine of theta. I can find sine theta very quickly. Okay, that's going to be the 4/5. If I didn't have that, there's probably no way I'm going to use this identity because it's not there. And I don't want to do more work than I have to do. This one might be the better option because I'm already given the cosine. I don't have to hunt and peck for the sine. I'm just going to use the identity and plug in the value. This one, I do have the cosine, but again, I do have the other issue of first I got to figure what sine is. And hey, I'm just too lazy, I guess. I don't want to figure that out. I'm given cosine, so I'll just use this identity instead. So I have 2. We're going to take the cosine, square it, subtract off 1. And then do a bunch of arithmetic and clean this thing up. What does that say about theta? Interesting question. Because what happened to the polarity of the cosine? It went negative. Guys, where is cosine negative? What quadrant could you be in? Quadrant 2, quadrant 3. So you took an angle, you doubled it, because remember it's positive up here. You double the angle, and where did it take you? From quadrant 1 to quadrant 2. So if you're in quadrant 1, what are the measures for theta? It's between 0 and 90 degrees, or 0 and pi over 2. When you double this, that's saying theta is somewhere between 0 and pi. Okay, that's a pretty big spectrum. Let's say if I'm at an angle of 30 degrees. If you double 30, you get 60. Cosine of 60 degrees, is that positive or negative? It's going to be positive because you're still in quadrant 1. You're still looking at an acute angle. You got to get past the threshold of 90 degrees before you turn negative for cosine. So what that's saying here, in a very implied way, where you have to read between the lines, here's your 45, pi over 2. Anything in this region, when you double it, it's going to throw you over into the second quadrant. Anything below the 45, between 0 and 45, if you double it, it's just going to send you potentially maybe up here, or it could send you still down here a little bit. It kind of depends upon what's being played out. But you're going to remain in quadrant 1. So quadrant 1, you stay there. This one's going to send you to quadrant 2. So things can take a little bit of a different turn here. So you got to pay a little bit more attention, a little more detail to what's happening with the thetas. Is it flinging you too much to one side or the other? Okay, now, with that said, I know I'm in quadrant 2. I really don't know what theta is, but I know it's going to be a value between pi over 2 and pi over 4. In the second quadrant, tangent's going to be negative. There is an identity, a double angle identity for tangent. I wouldn't waste your time with it. You don't really need to know that one. Why not? Well, you guys know the secrets. What's tangent? Sine over cosine. If you know these two, you know this one by default. And since I already know what's happening here, I'm going to take the ratio. I'll have 24 over 25 minus 7 over 25, and I'm done. There is an identity for the double angle for tangent. If you know it, that's great. It just speeds it up a little bit more in certain problems. But honestly, it's not really going to help you out that much. It just helps out ever so often. I guess it's kind of like if you get a flat tire in your car, it's great to have a spare tire when you need it. But you can always call it AAA or someone to come help you if you need it. Okay, it's a little extra baggage. So what you need to do is make sure you know the double angle for sine and for cosine. Those are definitely the things you need to know. There's going to be 3 of these, again, for the cosine. You can do some other things with sine, but typically it's going to be 2 sine theta, cosine theta. Okay, let me stop here, see if you have a question or a comment. Okay, so let's take the flip side of the argument. You got to find sine of theta, cosine of theta, and tangent of theta. And what we know here is cosine of 2 theta equals 4/5. Up here we see cosine of 2 theta. And right here I do see some identities for cosine of 2 theta. So it might just be natural just to take one of these and go along with it. So I can take the 4/5 and I can drop it in. And if I want to figure out the sign, I might want to just take this identity of 1 minus 2 sine squared theta. Don't forget the theta. It's just not that. That's going to be a sin for sure. Don't transgress. Make sure you do have the theta along with it. Solve. Maybe bring the 1 over to the other side. When you do that, you're going to be left with negative 1 over 5. So you can fill in the details. Take the square root. Okay, so when we take the square root, we're going to be left with 1 over radical 10 plus or minus sine theta. Should I take the positive case or the negative case? This is where I got to be a little bit more careful, a little bit more attentive as to what's happening. Look at the restrictions. If you were to multiply straight through by 2, you get the restrictions here for 2 theta. So for theta, you're between pi over 2 and pi. For 2 theta, you're between pi and 2 pi. What was cosine? Was that positive or negative? Positive. Guys, where is cosine positive on this region? Which quadrant? Quadrant 4. So I'm over here, quadrant 4. In quadrant 4, is sine positive or is it negative? It's negative. So we're going to have sine 1 over negative root 10. Okay, figure out the cosine. You could use the identity again. You can use this one. That's perfectly fine. You could go ahead and set up a triangle. That's perfectly fine. That would work. You could even use a double angle identity for sine. That would also work. But that's going to require you to figure out the double angle for sine of 2 theta, which we can do real quick. Let me just run through it to show you could do it. Sine of 2 theta, you have your triangle. And I'm not going to worry about the sine. We know what's going to happen here in the end. You're going to have the adjacency side, hypotenuse. You're going to come up with your 3, 4, 5 triangle. It's going to correspond to 3. That's 3 over 5. But you know the identity for the double angle for sine. That's going to correspond to 2 sine theta cosine theta sine 2 theta. You know this. Drop it in. You now know this. Drop that in as well. Can you solve for cosine theta? Absolutely. We had to adjust it a little bit here because we're going to be in quadrant 4. We'll use that. Remember, we had to decide if we're taking the positive or the negative. So it's a little bit of a fudge factor you have to kind of worry about, but this is what you would get here in the end. You get that. And if you want the tangent, you could go through the identities or just take the ratios. It'd be a whole lot easier if you do that, guys. And then clean it up in the very end. Do whatever you got to do. Okay, you could unsimplify this real quick. You would have 3 over root 10. Kind of check to see what I did there. But you're getting negative 1 over 3. That's interesting. All right. So make sure you spend some time going through these identities. Make sure you got these down. So next time you're ready to go. And we're going to keep using these identities, generate some other identities, and just keep going from there. We're also going to look at some more verification of equations. So you might want to go back and start reviewing how you did that previously. And then we're going to keep moving forward. You guys have a great day. I will see you next time.
I hope that today's lesson was a positive and an encouraging learning experience. and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.